model selection with two likelihood criteria called AIC and BIC. So before we begin, I want you to load these packages that are required. And while you load those, I'll just give you some background on these two criteria that we're going to be using. If you don't already have these packages installed on your computer, again, go to the Packages tab, click on Install, and then you can type in the name, mass or the car package, and then just click on the appropriate package and then install. Okay, so, and then once they're installed, just run the library functions. Okay, so AIC and BIC are both penalized likelihood criteria, and they're sometimes used for choosing the best predictor subsets out of a long list of predictors in regression models. So you use them in logistic regressions or multiple regressions. So AIC stands for I'm going to totally butcher the name, AIC information criterion, and that's an estimate of a constant plus the relative distance between the unknown true likelihood function of the data and the fitted likelihood function of the entire model. So a lower AIC value means that a model is considered to be closer to the truth. So the better the model, the lower the AIC. BIC stands for Bayesian information criterion, and this is an estimate of a function of the posterior probability of a model being true under a certain setup, usually a Bayesian setup, so that the lower the BIC, the more the model is considered to be true. So lower BIC, better model because it's more likely to be a true model. So AIC and BIC are both very similar in that they're measures of the relative quality for statistical models of a given data set. So by comparing the quality of one model to the quality of others, you're able to complete what's called a model selection. In other words, choosing the best model. Okay, so we're going to set our working directory. I have mine already written here, but if you need to set yours, you can go to the Session tab, click on that, go to Set Working Directory, choose Directory, and then navigate to whatever folder you have your files that are needed for this script or whatever data set you're running, and then select that folder. Okay, so for this, I'm going to use the Dodson data set. Just go through some of the summary statistics, see how it all looks. So for model selection, you can either compare models that you've pre-selected based on like preset hypotheses, or you can run a model that has all of the predictors in it, so you can kind of see how things are interacting. So we're going to compare 4 models that we've built, or I've built, that represents different hypotheses that I want to kind of test going into this tutorial. I'm going to run my models, and now that I've had my models made, I can run the AIC tests. So this one, I'm going to test the AIC by using the AIC function. So I'm going to test the AIC for model 2, and it gives me a value of 287.13. So you can also run the AIC function on all of your models. So this will give you all of the AICs for each model at once. So you don't have to sit there and keep retyping. It's kind of like almost like the tapply. So when we run that, so here are the AICs for each of the model. Now, again, the lower the AIC, the better the model. So this right here is the lowest AIC. So model 2 has the lowest AIC of 287.13. So in that case, that would be our best model. You can also use the step AIC. We'll get into this a little bit later. So that's another way. So what this does is it takes out different predictor variables and sees how that influences or changes the AIC, and depending on that, it'll tell you which model is better. If you remove one variable, it may decrease the AIC, so that model might be better than the model that has that variable in it. But we'll get into that a little bit more shortly. So the next thing we're going to do is this mule millin thingy. Mulemin, I guess. I have no idea what you would call it. So you can go ahead and install that, and R is going to yell at me because I already have it. And then just load up the library. Okay, so I'm going to take a look at the distribution of the response variable that I'm using from the Dodson set, and my response variable is the fish variable. So I'm just looking at it. Take a look at the distribution, make sure everything seems normal. From here, you can see there's a right-tailed skew, meaning that everything is kind of clumped over here onto the left side of the histogram. That's probably due to these outliers that are kind of pushing everything to the left. So you can try a transformation since things are not normal. So you can try a square root transformation, which seems to make things a little bit better. Shapiro test. So we get a p-value that's greater than 0.5, so that's good. That means that's normal. Let's see if we run the log, what happens. All right, so the log does not make things better in comparison to the Shapiro test. So you can use whatever transformation you want in this. I'm going to use the square root transformation because that gave me a high p-value for the Shapiro test. So I'm going to transform my fish variable and then add it to the data set. Okay, so let's create a global model using the transformed fish variable as our response. And to do this, we'll use a function called dredge, which will generate a set of models with combinations or subsets of terms in the global model. And then you have optional rules for model inclusion, or what's actually included in the model. So for this, the main option that I'm going to work on is this NA action. So there are some missing values in the Dodson dataset, and by using this coding or a function, you're able to prevent submodels. You're able to prevent fitting to submodels to different data sets. So you have to actually code this separately as I have it here, because the options coding cannot be put in the global model or the dredge function because it'll end up resulting in an error. So I'm going to run that and then run a full model that has all of the variables that I'm interested in investigating. Okay. So we can analyze the model then by using this dredge function. So I named my model full, so I'm going to dredge or analyze the full model with dredge. Okay, so models are ranked by AICC. So AICC is basically AIC, except it's used on infinite sample sizes, but it still pertains to the same or similar concept. The lower the AIC, the better. So the lower the AICC, the better the model. Okay. So when you do the dredge full, this performs an automated model selection with subsets of the supplied quote-unquote global model. And then you also have these other optional choices of other model properties. So you can also do different like link functions. So you can have all possible combinations, or you can have them tailored to the conditions that you specify. So according to this, the lowest AIC is this value here. So that means that these values are the most, not most influential to the model, but the most important. So your best model contains these two variables. And then you can see as you build different models, how that influences the AIC as you take out different variables and supplement them with others. And here, this is intercept, and that's just kind of a nuisance variable. But yeah, each one of these values is a p-value of the individual variable. Okay, so then to retrieve, so p-dredge is another thing you can do. It does the same thing. The reason why we're doing dredge instead of a p-dredge is because it can parallelize model fitting processes by basically using a cluster mechanism. So we don't want to do that. Okay, so we'll retrieve the models from selection table BIC per se. So we'll do that, and you can do that either using the get.models function and then running that on the dredge full, or model.average, AVG, average, and then incorporating the dredge models and dredge full. And both make sure that the subset is set to true. Okay. So again, this gives you the individual AICs and how the models, or I should say, each of the different model values, and it will give you the p-values for those coefficients. And then the same thing can be done with this. It kind of condenses everything, and so it gives you the full model versus the subset. So the subset being the model that the subset model that you're running. And then it tells you which models or which components are in the model to form that subset. Okay, so then we can run this. All right, so this gives you all of the p-values for those averages of the models. So you get your full model average, and then you get the conditional averages, which are for the subsets. And then you can also verify that with the confidence intervals. So works the same way, that you can determine if it crosses over, if it contains one or crosses over one, then you do not have significance. But if it does not contain one in the confidence interval, then you have significance. Alrighty, so that's just how you interpret. So that's not really for choosing the best model. That's once you've chosen the best model, understanding the importance of each variable that's in that new model or that subset model that you've now built, and whether or not that model is significant based on those variables. Okay, so there's another thing that you can do for model selection, and that's called the all subsets. So all subsets is actually this huge coding strand that you have to run, and usually you'll put it in its own separate script, and then you can source the code by running source, and then here, this function right here, source, and then quote unquote all.subsets.glm.r, or whatever you call it. This is what I happen to call it. Most people, I think, call it. I know some others that have this. So I have it included in here, but yeah, it's a huge function, so you have to manually code for it. Oops. Okay. So if you run that whole thing, that'll end up creating the all subsets function that you need in order, or coding in order to run the all subsets. So I'm going to use a new data set called Mallow. Okay. And just again, look over the summary statistics, see what's going on. So jumping ahead, just to save time. So the C3, they were comparing C3 and C4 plants. So the C3 is going to be the response, and it's not normal. So it has to be transformed, and it did well with the square root transformation. So we're going to end up creating a new C3.square root variable, which is going to be our new response variable, and binding that into the Mallow data set. So this is where I bind it using the cbind function. Okay, so now that we've done that, we can manually build some models based on preset hypotheses. So these are the models that I've built based on hypotheses or different areas of interest. So if you don't have, again, if you don't have preset hypotheses, or you just want to see how all the factors play into the model, then you can run a full model with all of the variables as predictors. And sometimes that's great to do because you'll notice that when you start running models and you take out certain variables that may be influential to another variable, such as when you're looking at immunoglobulin levels, and you start taking out different antibodies that are related to a certain antigen, or vice versa, you start to actually really influence how the model runs. So sometimes incorporating all of the variables will give you a better estimation of what the true best model is. These are things that I want to test, so I'm going to run those. All right, so now that I've constructed those, I can request the AIC values of each model. So I'll do that. Okay, so again, the lowest AIC is the best. So our lowest AIC is this here, meaning that our best model is a model that only contains latitude as, this is latitude, longitude, and then this is latitude and longitude. So our best model is the one that contains latitude only because it has the lowest AIC of -16. Okay, so we can also test or run the BIC. So the BIC function is a generic function that calculates the Bayesian information criterion. It's also known as SBC, the Schwarz's Bayesian criterion. They're one and the same thing. So it does this for one or several fitted model objects for which a log likelihood value can be obtained. And this is all according to a formula. I'm going to try to get it right here. -2 times the log likelihood plus the NPAR times the log of knobs. So NPAR and knobs, you're probably like, what is she talking about? So NPAR represents the number of parameters that you have in your model, and knobs is the number, or knobs, sorry, is the number of observations in the fitted model. Okay, so again, the lower the BIC value, the better the model. So running our BICs, I already gave it away in my script, how rude. Anyway, so our lowest BIC is in, again, model.lat with a BIC of -9. So your AIC and BIC should, again, they should parallel each other. They should reflect the same thing. The only time that you would have any great difference, or if you would have something that your AIC does not relate with the BIC, or does not agree with the BIC, sometimes that'll happen because the BIC penalizes I think, penalizes larger models a little more harshly than AIC. So if you have some large disparity like that, that could be the reason behind that. Otherwise, they should be just about the same or reflecting the same, which they are in this case. They're both reflecting that model.lat is the best model based on those criterion. Okay, so let's look at some other ways of model selection. So we've looked at these, looking at AIC and BIC. Now, what if you have a really big model and you're running this model on all of your predictors and you have many predictors? Well, it would be really annoying to go through each one and create individual models of different subsets or different submodels. So there's different selection methods that you can run. So let's first create a full model. So we're going to put in all of the predictor variables we have and test them against our response. All right, so the first one is something called forward selection, which works on single term additions. So basically you essentially have something plotted against something, and then you slowly start adding predictors in individually to see how your AIC is influenced. So there are several ways or several functions, that you can employ to run a forward selection. The first is to use the step function itself and set it to read for forward. So that's this here. So you have your response and you do this little squirrely thing and 1, because you're going to add one predictor every for every result that's run, or every model operation, I guess you could call it. And then you're going to set your lowest standard to 1. So it's going to have only one predictor, and that's going to be the lowest amount of predictors in the model. And then the upper is the model full. So that's the maximum amount of predictors that you can have, or the maximum parameter. And the direction is forward, because we're doing a forward selection. So you can run that. And with this, you can scroll through and find where your lowest AIC is. And usually, I think it's actually all the time, it's going to be your last value. So here are, ambulance. Sorry. Very exciting. Oh, that's actually a fire truck. Okay, I'm sorry. Okay, so here our best model is when we have the C3 as the response, and then we have lat, map, this thing, and this thing as our predictors. So that's what ends up giving you the best model with the lowest AIC of negative 228. Let me just make sure that's correct. Yep. Okay, good. Okay, so you can also do a forward selection using the add one or add term functions, and both work the same. So you start off with the same, basically the same coding, except in the add one, you have to include your full model, just so it knows the full parameters, because you don't give it this scope list kind of coding. And then you set the test for both of them. The test is going to be set to F, because you're running an F test on this. So you're still getting AIC values, but it's through an F test method, if that makes sense. Okay, so we'll run that. All right. So again, both of these will tell you roughly the same thing. You're going to look for the lowest AIC and see when that is obtained. So here you don't have the full model listed out. What it's doing is, so when you add in, when you start off with nothing, this is what the AIC is. When you add in the map predictor, you lower your AIC. You increase your AIC to negative 178.98. So each one of these, so this is what happens to the AIC when you include MAT. This is what happens when you include this. So at this point, right here, you have a model that consists of predictors map, MAT, and this JJA map. So you're adding to the previous. So by the time you get to lat, you have map, mat, this, longitude, and latitude all in your model. So this AIC looks like it pertains just for latitude, but it's not. It's for the model that contains latitude and all of these preceding variables, if that makes sense. Okay, so our lowest AIC here looks to be this value here, and it is significant. Let's see if that adds up, and that also matches this here. I don't think it matched what we did with the single term additions though before. No, it didn't. Interesting. Okay, but anyway, so those are two things you can do. And then, so we'll do a backward selection. So you can run the same tests, and what you'll end up changing is you keep the scope the same, you just change the direction to backward. Okay, so we'll do this backward for the step. And again, this operates along the same lines, but opposite of forward selection, in that you're monitoring influences to the AIC through single term deletions or removals. So this can be done, again, with the step function as I just ran. So if you wanted to see the results, if you did not want to see the results, sorry, for each step, you could add an argument to the code, trace equals false. So that way you're just seeing the best model. So it kind of takes you away from having to retrace your steps through that or sift through data, which is nice. So I'll just run it here just so you can see. Trace equals false. No, not trace plus, trace equals. Okay, so here you get only the best model. So in this, our best model is built on these three predictors. And if we look up a little bit, we can see that that reflects with this. So the best AIC value is -229.32, and that's obtained when you have these three predictors. Oh, there's another fire truck. This is when I just want to kind of follow them and start building bleachers on the side of the road and see what's happening, be one of those nosy people. Especially when they're sitting right outside your apartment. Oh, ADD's kicking in. Okay, so there's two other selection methods that you can do for backward selection. You can do the drop one or the drop term functions. So that conducts backward selection, again, using the F test. So almost like the same principle as what we did up here with the add one or the add term. So we're going to run those. Okay, so the last model has, nope, I lied. So again, we're going to look for the lowest AIC, which will represent the best model. So the lowest AIC actually looks to be right there. And then it actually increases when you start deleting out these variables. So it tells you basically the same thing as it does right up here, that your best model contains these three predictors. Okay. And I personally like the step models a little bit better because sometimes it's hard to actually determine what the best model is from the drop or the add terms because it doesn't specifically give you that model. It just tells you it runs through and then starts adding in or subtracting values and how the model influences, but it still doesn't give you that full model, if you get what I'm saying. Okay, so the last thing you can do is a stepwise selection. And this just goes through in both directions. Okay, so again, it validates or substantiates what we've said previously, that again, the best model is this model that contains these three predictors, and each one gives us an AIC of negative 229.32. Okay, so those are some selection methods. Now, there's also this thing called all subsets, which goes back to that huge thing that I loaded before. So we're going to try this. All right, so we're going to create or manually create a y value, manually create an x value. Just give it a peek, make sure it looks like what we want to have, which it does. These are our predictors. Hooray, things look great. Okay, so when you run an all subsets function, you run it on a y and an x. You don't have like an actual value to place in there. You need to assign values to y and assign values to x. And if you want to if you wanted only two variables to be compared in the models, or you wanted to limit your models to two parameters, then you can add in an argument to this function. Right after the x, you would do comma max p equals 2. So you could do, just write it in right for you, max p equals 2. And that would set it to only two parameters. Oops. Okay. So we'll run this. Okay. This is my favorite because it gives you everything in one easy chart to read. So you look for your lowest AIC, which should be, usually is the first statistic that it will read out. So here, our best model is that only contains latitude. So again, it shows you these variable importance using hierarchical partitioning, and then as well as the best models according to AIC. So what I want you to notice is that this uses maximum likelihood estimations rather than ordinary least squares, which is one thing to keep in mind when you talk. You'll know more about them if you've run like generalized linear models or something. But looking at the output, we can see that the first result is listed as the best model again. And it usually displays the models again from lowest AIC to high, so usually the first output or the first statistic in that output is the best. Okay, so you can also do this, well, before I jump ahead. So if you think that this is your best model, you can run it, make it an object, then actually get the AIC value of it, and then I'm going to run it again. So these two things, if you have AIC and then your model, AIC and then this k equals 2, they're the same thing. So AIC is denoted in R as k equals 2. I'm going to explain to you what that means in a second. So by default, this is already included as one of those internal arguments. So if you run the AIC function with or without k equals 2, you're going to still get the AIC reading for that model. On the other hand, you can manipulate the k value so that you can have the AIC function read out for BIC value instead. So what you have to do, well, let me explain that first. Okay, so what's this k thing that I'm talking about? So k equals the multiple of the number of degrees of freedom used for the penalty. So in AIC, that value is equal to 2. for BIC, BIC is defined as K being equal to the log of the knobs, remember the number of observations, of an object, or whatever object you have. In other words, it's the log of n observations. So this needs the number of observations to be known. So you can create a value for K equals log n, where n actually equals the number of rows in your data set. And that's what I usually do. So that's what I do here. I create a new object called perrule.n, meaning the n value for perrule. And I'm doing that by finding the number of rows that are in this data set. And so the number of rows becomes this object. So then I can create the IAC function and test it on the best model, or model best, which is this model up here, my lat model, and then run the argument k equals log of the n of my object. So the n of my object is the n of the perrule trans, which I've coded into perrule.n. So it would be k equals log of perrule.n. So that's how I can get the BIC using an AIC function. Okay, so this gives me the -9. Now, if you remember, these look very familiar. Well, that's because we've already seen them. We ran them before earlier in this tutorial. So yeah, so if we can also run an actual model selection with BIC instead of AIC. And again, they should both tell us about the same thing, unless there's a huge penalty difference, but it's still neat to see it done both ways. So in order to run a model selection for using BIC instead of AIC, we're going to use the step AIC function. And you're going to recognize that this LM, and then you have your full model here, and then your scopes, because so you wouldn't run this on the model that this lat model that I have up here, because this is already determined as our best model. This is, again, doing model selection. So we go back to the full model. So you have the same parameters as we saw previously with the forward and backward selection. You have your lower limit is 1, upper is this model full, but the direction is set to both, and the criterion is set to BIC. And you make sure that you have k equals log and then whatever the n object you create. So in my case, the n object is the n-row perrule trans, which I created to call perrule.n. So I'm going to run this. All right, so it gives us what we had before. Now, the BIC and the AIC, the actual numbers themselves, are going to be off. And I mean, they can be off anywhere from 5 to 10 values. I think the one we had before was off by like 7 or something. So that's okay. But as long as they tell you the same thing, which they should be, unless there's a penalty difference. But here we get the same thing that was determined by running the stepwise selections or model selection methods using AIC. But the best model is this model here that has 3 predictors, the JJA map, DJF map, and lat. And that gives us here, so this isn't, it tells you AIC, but since we criterioned it for BIC, our BIC value for this model is -220.16. All right, so there's this thing, a lot of this is all just deciphering numbers, but there's a way to actually see this visually. You can't, you can only glean so much information from it, but it's still neat to see. So it's using the leaps package and the regsubsets function. and it's called the best subsets method. So you have to install the leaps package if you haven't done so already, and then run the library for it to actually bring it up. So then you can run this function called regsubsets, and you run it on your full model, and then you can set this for whatever parameter you want. I'm going to set it for 2, and you can run that, and then you can pull up the summary of it. Okay, so you can do this for adjusted R² or for the BIC, either one. You just have to code for it. So you can do that by saying scale equals, and then here this is adjusted R², and here this is BIC. So the reg subsets plot here shows the adjusted R² along the x-axis for all these different models that are created by combinations of variables that are listed here on the x-axis. So for instance, you can draw this imaginary horizontal line along the x-axis from any point on the y-axis. So let's say we draw a line like right here. So there's this imaginary line here, per se. Actually, we'll put it right here. Okay, so that line would correspond to a linear model where the black boxes that touch that line form the x variables. So here, let's say here, okay, so we have an imaginary line that runs right here. So it starts at, it runs from this x-axis value of 0.46. So the black boxes that touch it, well, we have our intercept, which is not very exciting, and then we have lat. So the model that contains lat gives us an adjusted R² value of 0.46, meaning that when you have just latitude, if in that model, if you have a model that's just built with latitude, that model alone counts for 46% of the variability of the full model. Remember, adjusted R² tells you the percent of variance that model accounts for of the whole model. And you would do the same here. So if you drew a line like right across here from -33, that would mean in order to get a BIC value of -33, that model would include, obviously everything includes the intercept, but it would also include the mat, the JJ app, your DJF map, and latitude. So that's how you can visualize it. It doesn't tell you, it allows you to visualize these relationships, but it doesn't necessarily tell you whether or not they're statistically significant. So you can't predict a lot or predict significance from the models. You can just visualize the actual relationships in the models. Okay, so last but not least, there's this, so AIC and BIC they're used primarily most of the time. Adjusted R² can get skewed a little bit, so that's why AIC and BIC are used heavily. But there's also this thing called Mallow CP, which also falls to the wayside, just in this huge movement towards AIC and BIC. But it's one of those things that does exist that you could still use if you wanted to. So for that, you also have to use the leaps package. And I should shrink this down again. Okay, so what you do is you have to first you have to code what predictors you want for X. So for this, I'm going to make a small model, or I'm just going to have columns 3 through 5 represent my predictors. So that would mean map through JJA map. So map, mat, JJA map are the predictors that are going to be used in my model, testing against my Y value, which I'm assigning to column 9, which is your C3 square root. So the names that I want to assign into the leaps, especially for these guys over here, correspond to your X parameters. And then the method that I'm using is CP for this Mallow CP criterion. We can run that. Okay, so the first part of the output, which is denoted with this $which, lists the 7, based on what I've coded here, the 7 possible submodels in 7 different rows, because there's 7 models. So I'm sorry if you hear other talking in the background. It's the firefighters that are outside my apartment, and of course I'm really interested in what's going on, but I have to focus. Okay, so back to R. All right, so sorry. Okay, so these are the 7 possible submodels listed out in these rows. So the first column indicates the number of predictors in the submodel for each row. So that's this right here. So here you only have one predictor, and you know which predictor it is based on whether it says false or true. If it says true, that means that variable is being included in the model. If it says false, that variable is not. So here we have a model that includes one variable, and that variable is math. Okay, so then you have this crucial information that's also given or yielded by this quote-unquote size and CP values. So obviously CP is representative of the Mallow's CP criterion. So that's what that CP value gives. It gives it for the Mallow CP criterion for each submodel in the same order. So this would be, so this corresponds to this corresponds to this corresponds to your third model, and this corresponds to your fourth, and so on. And then, so it gives it in the same order, and then you have this size value here. So size gives P, and P represents the number of parameters in the model. So the best submodel is the one in which the CP value is closest to P. So based on that, the best model given this output is the last model, or the 7th, because the CP here is 4 and the P is 4. However, that is the full model, so it includes all of the predictors that we are testing. Now the full model will always have CP equal to P. So we want to find a suitable reduced model, essentially the second best thing. So we recognize that this, yes, is the best model according to the Mallow CP, but we want to find the most suitable reduced model, which means not the full model, the second best thing. So with that in mind, the fourth model is actually the best, this one right here, because it gives a CP value or criterion of 3.779, and that's almost equivalent with its P value or P parameter of 3. So instead of using the Mallow CP criterion, you can also use the R-squared or adjusted R-squared criteria using essentially the same formula. So you just code in method equals R2 or method equals adjusted R2, respectively, in place of method equals CP from the last argument. So I have that right here. I'm going to use the adjusted R-squared, and I'm going to use almost the exact same coding except for that. You can run that, and you interpret it the same way. Sorry, you don't interpret it the same way. Well, you do and you don't. Okay, so for adjusted R-squared, the highest value is going to have the best adjusted R-squared, so that's going to be your your best for that criterion. And then you can tell this p size of it, which doesn't, or yeah, the parameter size of it, which doesn't really relate here since you're not doing it's not like your best model selection is based on a ratio between the two. But you can interpret this the same up here on what parameters are actually included and which are not. So yeah, that's how you can do model selections with AIC, BIC primarily, and then with some other fun things. And hope that all makes sense and that you have fun selecting your models.